My name is Duccio Testa, and in this lecture we will be discussing plasma waves in the ideal MHD model. We will start with the general formulation for the ideal MHD waves, and then we will study the three classes of waves that are supported by the ideal MHD description of the plasma: the shear Alfvén waves, the fast compressional Alfvén waves, and the slow magnetosonic waves. Now, to obtain the general formulation of ideal MHD waves, we start from the ideal MHD equation. Then we add a small perturbation to a uniform and static equilibrium. We linearize the original system of equations around the equilibrium. We apply Fourier transform, and then we obtain the wave dispersion relation. Now, we start from the ideal MHD equation, and we use them to eliminate J and D. We have here Ampere's law and the momentum balance equation. We can take J from Ampere's law and plug it into the momentum balance equation. With this procedure, we eliminate J. So what we obtain is that ρm dV by dt is equal minus grad P plus 1 over mu naught the curl of B cross B. We have then Faraday's law and the ideal Ohm's law. We can take the electric field from the ideal Ohm's law and put it into Faraday's law. So what we have, dB by dt equal the curl of V cross B. We then have the continuity of the plasma mass and the equation of state. We can then consider a uniform and static MHD equilibrium to which we add small perturbation. The magnetic field with an equilibrium term B0 plus its perturbation B1. For the fluid velocity V, since we consider a static equilibrium, the equilibrium term is 0, we only have the perturbation V1. For the mass density, the equilibrium term is a constant, perturbation ρm1, and the same for the pressure, P0 is a constant. We can then linearize the initial system of equations around the equilibrium. What we obtain is that dB1 by dt is equal to the curl of V1 cross B0. Perturbation, perturbation, first order. We do the same for the continuity equation, d ρm1 by dt plus ρm0, the divergence of V1 equals 0. The momentum balance equation, ρm0 dV1 by dt minus grad P1 plus 1 over μ0, the curl of B1 cross B0. And then we have the perturbed pressure, P1 equal gamma P0 over ρm0 times ρm1, the perturbed mass density. This factor appears in the last equation, gamma P0 over ρm0 is the sound speed Cs square. Sound speed Cs gamma P0 over ρm0 squared. So the perturbed pressure P1 is equal to the sound speed square, Cs square, times the perturbed mass density ρm1. Now we can apply Fourier transform in space and time to linearize equation. So our first equations become minus omega B1 tilde, the tilde indicates that we are now in Fourier space, K cross V1 tilde cross B0. For the mass density, we have minus omega rho tilde M1 plus rho M0 K dot V1 tilde equals 0. We have then for the momentum balance equation minus omega rho M0 V1 tilde minus K Cs square rho tilde M1 plus 1 over mu naught K cross B1 tilde cross B0. And finally, for the perturbed pressure, P1 tilde equal Cs square rho m1 tilde. We can now choose our geometry for the waves. Without loss of generality, we can take the equilibrium magnetic field to be along the z-axis and take the k vector in the xz plane. We now have two cases. The first case is the case of transverse wave, where V1 is perpendicular to k. This case is depicted here in this figure. The equilibrium magnetic field B0 along the z-axis, the vector k in the xz plane, and there is an angle theta between k and B0. The perturbed velocity V1 in the y direction perpendicular to k. The second case are waves with longitudinal component, where V1 is also in the xz plane, which is depicted in this second figure here. Now let's look at transverse wave. V1 only along the y direction, and therefore V1 is perpendicular to k because k is in the x and z plane. We can now start with the equation in Fourier space for the perturbed mass density. Perturbed mass density rho tilde m1 equal 1 over omega rho m0 k dot v1 tilde. But k and v are perpendicular to each other, therefore also k and v tilde are perpendicular to each other, so rho m1 tilde equals 0. There is no perturbed mass density. Transverse waves are non-compressional. We have then two remaining equations that link B tilde one way and V tilde one way. So we end up with these two equations: omega rho m0 V tilde one way plus kz B0 over mu0 B tilde one way, and the second equation kz B0 V tilde one way plus omega B tilde one way equals 0. We can then combine these two linearized equations into a matricial form. Now we want to obtain a non-trivial solution which have a B tilde one way and V tilde one way both not equal to 0. And we obtain this solution by taking the determinant of this 2 by 2 matrix to be equal 0. And this leads to the dispersion relation for the shear Alfvén wave. This dispersion relation, there is a term very important, this quantity here, B0 square divided by mu0 rho m0. This is the square of the Alfvén speed, Ca. We can then cast this dispersion relation in a way that we see the Alfvén speed and the angle between k and the equilibrium magnetic field. This is the final form for the dispersion relation of the shear Alfvén waves. Omega square equal k square Ca square cos square theta. We can now summarize what we have found for the shear Alfvén wave. The shear Alfvén waves are transverse wave. The perturbed velocity v1 is perpendicular to k and to the equilibrium magnetic field B0. The shear Alfvén wave is non-compressional. The perturbed mass density rho m1 is equal to 0. The dispersion relation can be cast in a form omega square kCa square times cos square theta. To give you a bit of heads up of topics that will be discussed later in this course, the shear Alfvén wave is important in DT fusion plasma because the velocity of a fusion-born alpha particle whose energy at birth is 3.5 MeV is super Alfvénic, exceeds the Alfvén speed Ca. Therefore, alphas becomes resonant with shear Alfvén waves during their slowing down. Shear-Fein waves are ubiquitous to plasma, and in fact they were observed first in space and then in Mercury plasmas. Now let's look at ideal MHD waves with a longitudinal component. V1 now has an X and Z component, so K dot V1 is no more equal 0. We can repeat all the previous calculations to obtain an expression for the perturbed magnetic field B1 V1x B0 over omega K cross E way. We can continue the analysis and we obtain a dispersion relation for the ideal MHD waves with a longitudinal component. This is our dispersion relation for ideal MHD waves with a longitudinal component. We see that it has terms that depends on the Alfvén speed Ca and on the sound speed Cs, and it's in fact a quadratic relation for omega square. We can solve this equation rather easily. So we immediately see that there are two roots of this dispersion relation for omega square. We have a root with the plus and a root with the minus. We can simplify this dispersion relation because the ratio between the sound speed Cs and the Alfvén speed Ca square is usually much smaller than 1 in typical plasma conditions. So we can take only terms that are first order in the ratio between Cs square and Ca square. So we end up with this formulation for the dispersion relation: omega square 1/2 K square Ca square 1 plus Cs over Ca square, so a first correction in Cs, 1 plus minus the two roots for omega square, 1 minus 2kz square Cs square divided by K square Ca square. We can now consider the plus roots of the dispersion relation. We can now proceed with this calculation by summing 1 and the brackets. We can now take the product between two brackets and keep only terms that are linear in the ratio Cs over Ca square. And now we know Kz is K cos theta. We can then recast this last term. So this is the final dispersion relation for the plus root of the dispersion relation of ideal MHD wave with a longitudinal component. We call this wave the fast compressional Alfvén wave. We have seen that it's compressional, K dot V1 not equal 0, and it is the fast solution because the phase velocity is Ca, the Alfvén speed, that is much larger than Cs, the sound speed. We see the dispersion relation is simply omega plus square K square Ca square, and that the sound speed and the angle between the K vector and the equilibrium magnetic field only enter as a small correction. Now we have worked through the fast wave solution, the plus solution. Now we can take the minus solution. This will lead us to the slow wave. We've taken here the minus solution. We can now work through the algebra. The 1 minus 1 term cancels out, so we only remain with 2kz square Cs square divided by K square Ca. K square Ca and K square Ca simplifies out. So what we end up with, omega minus square, kz square, Cs square, and this is why we call this wave the slow wave, because the phase velocity is Cs, that is much smaller than Ca. The wave frequency depends on the sound speed and the angle between the k vector and the equilibrium magnetic field. So we call this the slow magnetosonic wave, a sound wave that exists in the presence of a magnetic field. A very useful way to represent the solution of the wave dispersion relation for ideal MHD is the surface described by the phase velocity vector omega k divided by k square. We have here on the left the case for the shear Alfvén wave, which is non-compressional, the dispersion relation omega square kCa square times cos square of theta. So if we draw this curve, what we see is that we obtain an 8 along the axis of the magnetic field, and the effective radius of this 8 is Ca cos theta. The second case, we have the dispersion relation for waves which have a longitudinal component. We have an inner figure that is again another 8. This corresponds to the slow magnetosonic wave, for which the dispersion relation is omega square kCs square cos square theta. The radius is Cs cos theta, so it's much smaller than Ca cos theta. The outer circle corresponds to the fast compression Alfvén waves, for which the dispersion relation is omega square k square Ca square when we neglect all correction due to the sound speed. So this is a circle whose radius is Ca. We can now summarize what we have discussed on ideal MHD waves. The first wave that we discussed are transverse wave. These are non-compressional wave, is the shear Alfvén wave. And this wave will be discussed in the context of burning plasmas. Then we have discussed compressional waves which have a longitudinal component. And we found two solutions, the fast compressional Alfvén wave and the slow magnetosonic wave.